Okay, this week I want to talk more about simple linear regression. I made a couple references to it in the introductory video that was posted early in the class, but I want to spend a little more time talking about it and going through some details that I think will be helpful for both simple linear regression and multiple regression. So we'll talk a little bit about what it means to be linear, the importance of accuracy in the model, some of the notation that we use, and also the use of it as a predictive model. So what is linear regression? We gather data, transactions, scientific data, etc., and we determine the relationship between parts of our data. We calculate the accuracy of those relationships and their consistency, and we determine something called an intercept, and I should actually say slope, not scope. Forgive me for that typo. Also known as a coefficient. And we build a model that will predict future behavior. So why do we do this? So past behavior is suggestive of future behavior. It's often very suggestive of future behavior. And that's when we can look at the relationship between variables in past data sets and make fairly accurate predictions, depending, of course, on the nature of those variables, as to what they're going to look like in future data sets. So if you read in Siegel, you've read in Siegel, he talks about human behavior is actually surprisingly predictable, maybe not necessarily on an individual level, but can be predictable as a group, or it could be even predictable on an individual level. So if we know the value of one variable, we can accurately predict the value of another variable once we know the relationship between those two variables. So we're learning from our past data and we're using it to make decisions. I talked early in the introductory video about Dolbear. So Amos Dolbear claimed in 1897 that there's a relationship between crickets chirping and temperature. So the higher the temperature, the faster the chirping. So he had two questions. One, how can we describe temperature changes given the number of cricket chirps? And two, can we use chirping to predict temperature? So he tracks his data. He's got an X variable and a Y variable. And the X variable, in this particular case, turns out to be the predictor variable. And what we are predicting is we're predicting temperature. So he tracked this information. He tracked the number of chirps that he heard, and then he tracked the temperature, and he used that to build a model. So each row is a different observation at some point in time. And we've counted the number of chirps per minute and the temperature, noted the temperature. So we'll call Y the temperature in Fahrenheit and X the number of chirps per minute. And we can plot them. So if we plot them, we have on the horizontal axis, we have the number of chirps, and on the vertical axis, we have the temperature in Fahrenheit. And this small sample of data, and mind you, it's a very small sample of data used for visualization, would not make a good model because there's not enough data. But it looks like it follows a diagonal line. Now, the diagonal line, or the diagonality, I should say, of that line, tells us a couple of things. One, it tells us that there is a pretty good relationship between the number of chirps and the temperature. If there wasn't, then those points would be scattered all over the plot, and they wouldn't necessarily fall into a nice clean line. What it also tells us is that there is a linear relationship between chirps and the temperature. So when chirps go up, the temperature usually goes up a predictable amount relative to the number of chirps. So it fits nicely into the scatter plot, and we're able to visually see that there probably is a fairly high correlation, a good linear relationship, and there's a strong kind of connection of these two variables to each other. So we want to draw something that's called a trend line. And the trend line is going to be the best prediction for at any number of chirps. It'll be the best prediction for what the temperature would be based on these data points. So we're going to draw a line, okay? And what we want, like I said, the best line, the very, very best line. And the way that we come up with the very, very best line is we build a line, draw a line, a trend line, that is as close as possible to every data point. Okay, let's talk about what that means. As close as possible, that makes sense. But the to every data point means all of the data points, and there are 7 data points here, as close as possible to all of them. Okay, that means that if we adjust our line to be as close as possible to this particular data point, are we going to lose the closeness that we had to this particular data point or to this particular data point? So again, we're going to draw a line that is as close as possible to every single data point. With 7 data points, that's not that hard. But imagine if you had 7,000. That's going to be a little bit harder. So that's not going to be a good solution. That's a better solution. That looks like it could be a good solution. That's not so good. Okay, so it becomes like this, how do we draw the best line? And the line matters because the two values we're seeking in order to build our model are going to be something called the intercept and the slope. And those are both products of the line that we draw. So simple regression, also called classical linear regression or bivariate regression, is a technique for fitting a line to a scatter plot of data. It's exactly what we were just trying to do, trying to fit that line to that scatter plot of data such that it is as close as possible to every single data point. The line can be viewed as the best line for the purpose of describing and predicting quantitative variables with an outcome, and it gives us the estimated mean outcome for each value of our predicted variable. That's a whole lot of math speak for basically saying at any level of chirps, it's going to give us the most likely value for temperature. And it's much better than eyeballing and drawing a line. So what we're doing when we actually take the two variables, in this case chirps and temperature, and we put them into a linear modeling tool like the one we would use in Python, it is going to return to us the values that will give us a line that is as close as possible to every single data point. And it will also give us the intercept, which is where the line begins, and the slope, which determines how steep the line should be from the point of origin. Here could be a really good example. So we dropped these 7 data points along with their value for chirps and their value for Fahrenheit into a linear regression model like the one we're going to use in Python, and it spit back 2 values for us. The first thing it spit back was the intercept. The intercept is the spot on the vertical axis where the line crosses the vertical axis. In other words, it's also the spot where the chirps are the lowest. In many cases, it's 0. In this case, it's not because chirps could go way beyond that. But the best way to remember intercept is a place where it crosses the vertical axis, where it starts, where the line begins. And the intercept is calculated based on the amount of how much you go rise over run. So basically, how high do you go and how far do you go over? So rise over run gives you a singular value that just basically determines how steep your line should be. So the 2 values that come out of a linear regression model are going to be intercept and it's going to be slope, otherwise known as coefficient. And since there's only one variable in this particular model, there will be one coefficient or one intercept. So how do we look at this? Okay, a line can be fit to a scatter plot of data just using 2 values, an intercept and a slope, just like I've said. So you may have learned this in high school using this algebraic equation, y equals mx plus b. Okay. In this particular case, m is the slope, that's the rise over 1 that I talked about, how steep the line should be, and b is the intercept. So we take a value, which is y, this is going to be a predicted value, and it's going to turn out to be our value of x times the slope plus the point of origin on the vertical axis, or the intercept. Sometimes the y-intercept is simply called the intercept or the constant. However, we'll use slightly different notation than y equals mxb. So some of our notation for our data, y are the raw actual values of the outcome. X refers to the raw actual values of the predictor. We index these using the sub I. So if this is y1 and x1, then we're looking at these values here. And y2 and x2, we're looking at those values there. So we just that's how we basically differentiate. And sometimes we drop the i's just to clean up the equations. So we don't necessarily need to actually have them there. So here's another way that we're going to look at this. We'd already looked at the y equals mx plus b. Now we're going to look at this a little bit with a different notation. And here's why we're going to do this with different notation. Okay. Well, we are going to look at y hat I. That is going to be, let's assume that the I is equal to 5,000. It's just a placeholder for which of the rows in the data set we're looking at. The y hat is a predicted y. Okay. Y without the hat is the actual y. Y with the hat is the predicted y, or the estimated y. And it is going to be equal to, there's a b, sub-zero, which is your intercept. That's a notation for intercept. That's what we look at B up here. It's the same thing. And we switch places here. So the plus sign is in the middle, and the B sub 1 is going to be your slope, and it's going to be multiplied by the x value at the 5,000th row. So let's take this with kind of backwards. We're looking at row 5,000. So take the value, the x value for row 5,000, multiply that by the intercept. We will multiply all of the rows by the same intercept, and we'll add the, I'm sorry, that's slope, not intercept, and we'll add the intercept, the same intercept. So it's the same intercept, it's the same slope. The only thing that changes here is x, and that means that the predicted value of y will change relative to x, hence the linearity of this particular equation. So y hat refers to the values of our outcome that lie on the line that we drew. X is our predictive variable, b is the intercept, sometimes called the constant, and b1 is the slope. So let's look at our cricket data. So we can find the intercept and slope for the simple linear regression line when we run this through a tool. This is, I believe this is, yeah, this is the one method of doing this in Python. And then we can go ahead and print this out. We'll print out the model. So we've just created a model, right? We use linear regression, and we fit it with these two variables, the two variables that are coming from our data set. So what it's going to do is it's just going to build something called the linear model, and we're going to put it in this variable called model. Maybe not the greatest name to call it model, but we can call it anything we want. We could call it crickets if we want. And when we go ahead and print out the two values that we need, we'll print out model.intercept, and that gives us our intercept, and we'll print model.coefficient, which is really our slope, but we're calling it coefficient, and that's what Python calls it. So when we determine the line that we want to draw to show the relationship between cricket chirps and temperature, we start on the vertical axis at 37.68 or 6786, and we then multiply each instance of x by 0.23 to determine how rapidly the x line will increase as you move from left to right. So B0 and B1 are really oftentimes both called coefficients, and this becomes more important as we get into multiple linear regression, because B0 in multiple linear regression will still be the intercept, but you may have B1, B2, and B3 if you have three predictor variables, each of which is its own slope. But we'll worry about that later. Let's just worry about B0 and B1 for now. So the line could be expressed as such. So y for any value, a predicted y for any value, is going to be equal to the intercept plus the slope times the x for that particular row. So the y predicted for that row is going to be equal to x predicted, or x value for that row, multiplied by the slope and then added to the intercept. And in this particular case, the numeric value is 37.68 plus, our coefficient here is 0.23, times x for each of the rows that we have on our data set. So any one point on that line is governed or given by that particular value, right? So, and we're not looking at the data points here. Here what we're looking at is just this line, right? So we determined what the best fitting line was, and then we came up with the numerical values that gave us that best fitting line. And we saw that there were 37, I believe, and the other one was 0.23. So now any prediction we make for any of these values is going to drop something on this line only. All predictions, every single predicted value will fall on this line. Okay? Well, that's pretty good because they're pretty close to the actuals. These dots here, the points, are the actuals. So we can see that there's a pretty good relationship between the predicted variables or predicted values and the actual values. But it's important to note that every time you look at a predicted y for any one of the values, it will fall on this line. It will always be on that line. It's going only later when you actually get the actual values for y that you can start to determine how good was my prediction. The intercept, when xi equals 0, the intercept is when xi equals 0, and that actually only applies in certain cases. So quite often what you'll see is you'll see the 0 point starting here, and so that means basically when chirps is 0, then your temperature is going to be 37. And that actually seems to work here as well. So what this is pointing out is that when we have no chirps, crickets as quiet as you can be, we think the temperature is about 37 degrees. Okay? That's what the prediction is going to be. Each time the amount of chirps increases by 1, we are then multiplying that value by 0.23 because 0.23 is the coefficient for the x variable. So that's just a little bit more mathy way of being able to say how do we account for the intercept. Well, the intercept is when the value on the horizontal axis is set to 0. So in this particular case, B0 is 37. We calculated the rise over the run, which is actually how much is the rise over how much is the run. And this is all done for you. So you don't have to worry about any of this. Python's linear regression tool will spit all this out for you. And this is just by way of explanation of how it does it. There's your rise and run. And so it gives us about a 0.23 value. And really what the tool will give you is it will give you the intercept and it will give you the slope. It doesn't make you care about the rise and the run. None of that is important. You'll get the intercept and the slope, and you can do whatever you want with it from that point on. Okay, so here is simple linear regression using cricket chirps. We start at 0.37 because that was our intercept. Okay, and then for every step over from 0 to whether it be 50 or 100, we increase by 0.23. So assume x is 0. That's going to zero this whole section out, and we're going to get 37. Assume x is 1. We're going to get 37 plus 0.23 times 1, which is going to be 37.23. Assume x is 2. You're going to get 0.46, and you're going to add that to 37, and that's going to be your predicted value. So for each numerical increase here, we're going to be adding on another 0.23 multiplied by the value of x. Add that to the 37, which is our starting point for the line. That's how we get our predicted values. And I'm going to skip through this because, okay, so we're now ready to use our line for description and predicting. Expected temperature, as we've said, equals intercept plus slope times the number of chirps per minute. Or the language of algebra, our predicted y equals our intercept plus our x value, or our x value here, times our coefficient or our slope. Our fitted line is, can't see it because it's off the screen, but you get the idea. Okay, our line is a model. You can think of our simple linear regression line as a model of reality. Okay, we're using the intercept and slope to approximate a process that we observed in the world around us. But it's not always a good model. Sometimes they're not great models at all. Sometimes they're really good and sometimes they're really inaccurate. Okay, but what are we modeling? This is a little bit more sort of visual about our model. Remember, our model is predicted y is equal to 37. This is more exact numbers, 37.68 plus 0.23 times x. Okay, so we can work through this and see. We already talked about when it's 0, the intercept is 37, so we see how that line works. The intercept is the expected mean of the outcome when x is 0. Okay, let's break this down. We talked about the intercept being the value when the x value is 0. We saw that visually here. When x is 0, where the line falls, the value on the vertical axis is the intercept. Okay. Why does it say mean? It says mean because what you're doing is you're building a whole lot of lines. You're building a whole lot of examples. And when the regression process works, it will work through multiple instances of trying to find the best fit of the line. And that's why it says mean. It really comes out to be mean not that much. It's not that important that we're using mean. It is a predicted value. And that's what it is on any part of the line is going to be a predicted value. But there is an averaging process that derives it, and which is why you'll sometimes see it's the expected mean. The slope is the difference in the expected means of the outcome for a 1 unit increase in x1. Okay, so that's remember the 0.23? Every time we increase x by 1, we increase the slope by 0.23. So 0.23 times x1, 0.23 times x2, 0.23 times x3. And if your x turns out to be a value of 25, then you multiply 0.23 by 25, you add that to the intercept. A positive slope indicates an upward line. while a negative slope indicates a downward line. We haven't talked about a negative slope yet, but it's possible that these variables can actually have a reverse impact on each other. For example, the increase in one causes the other one to decline in a predictive and regular manner. And that will happen in certain instances. You can think of a million examples of when one variable increases, the other one tends to go down. For example, the amount of time somebody spends in leisure has a negative impact on their maybe their GPA or something like that. And that would be something that you potentially could model using a linear model. This is what you might see, something that looks like what you might see. This is actually done in R. It looks similar enough to what we'll see when we do this in Python that I didn't really make much of a change here. But we did a call. This is the R code actually. You'll see the in another video, you'll see the code that we use for Python. Python's actually easier. Gives us a lot of advantages over using R. But anyway, when we call this in R, it'll dump out what we need. It gives us our two coefficients. The first one coefficient is intercept, and it's 37.6886, or 6786, I should say. And then the chirps is 0.2307. It knows chirps because that's what we fed in here. We said, give me Fahrenheit as a function of chirps, and data set is equal to crickets. So it's going to say, okay, well, here's your predictor variable. And as your predictor variable, I'm going to give you a coefficient that will allow me to determine what that value should be at any point in time. The intercept never changes. It will always be the intercept. It's the point on the vertical axis where the line begins, or where x is equal to 0, and it never changes. But the chirps will change each time x changes. I'll skip over these because I just talked about all that. So we've been viewing linear regression as a descriptive model. That is, our line is giving us the expected average of the outcome given some value of the input variable. A similar approach is to think of our line as a predictive model. So if we were to go outside and count the chirps, could we predict the temperature? Well, here are a couple of examples of how we could do this. What would we predict the temperature to be if the number of chirps is 103? So here's our model, just like it has been before. We've abbreviated a little bit, rounded up, rounded down actually. And what we're going to do now is we're going to remember that the intercept never changes. So we always start with that same intercept. But we're going to take our coefficient and we're going to feed in our x value. In this particular case, that's 103. So 103 times 0.23, because remember, each time x goes up by 1, we multiply it by 103. So now x has gone up 103 times. So we multiply 0.23 by 103, add to it the 37, and we come up with a prediction of about 61 degrees. So over here is about 103. It's kind of over here, and we're looking up, and it looks like right around 61 degrees, sort of 61-ish degrees. Now, if we had an actual value, it probably would be pretty close, but it may not be exact. Let me see how that works. Oh, but our actual value, as I was talking about, we said 61 degrees is our prediction, but our actual value turned out to be 63.5. So this gets into the whole idea of how accurate the model is, because we're basically making estimates or guesses. It's important that we try to be as accurate as possible. And look at this value here. This is our predicted line. Remember, every prediction that we make is going to fall on this line. And it was built using this data. But the problem is that this is quite a ways away from that line. So that is what we call error. There's error built in every model. There's error inherent in every model. And sometimes we can look at it on a point-by-point basis, and sometimes we look at it in aggregate so we can determine how accurate the model was. So the difference between our actual values of y, once we have them, and our fitted or predicted values of y is called the residuals or errors. And it's noted by an E that's kind of hiding behind the graph there. So that's what we have here. We have a predicted value of 61, but the actual value turned out to be 63.5. So that means we're about 2.5 degrees off. That's a pretty big margin to be off, but it doesn't mean that they're all off that amount. Every one is going to have a separate error. Every data point is going to have a separate error, and some of those errors could be very, very small. So each observation has its own predicted y. And then for every x, there's a predicted y, which is equal to the intercept plus the slope times whatever x we chose, gives us that value. We can do the same thing here and the same thing here. All you're seeing is three different variables or three different values for x. For every x, we get a different y. We get a different predicted y. Our residuals are going to be whatever we had that was the actual minus the predicted value. And this is basically y hat. This is the equation for y hat. So in this particular case, our first residual is going to be our prediction minus our actual, or negative 1.86. Then we have 0.55 for the second one. We have a positive 2.06 for the third one, positive 1.45 for the fourth, negative 0.28 for the fifth. That's pretty close to the actual prediction. Negative 1.16 for the sixth, and positive 0.34. So we have a couple of them that are pretty close to the prediction. We have one or two that are a little bit far from the prediction, but this is a very, very important and powerful part of making predictions using an analytical tool, simply because we need to know how far we are either close to the prediction or how far we are off the prediction. And the reason why we do that is because if we have an idea that the model is pretty close to what we are trying to predict, that the actual prediction is pretty close to the actuals, then we know how much we can trust the model when we use it on future data. If, however, though, we see very large residuals and the model is just kind of all over the board, then that's probably not a great model. And in this particular case, despite the fact that there's only 7 data points, in this particular case, the model doesn't seem like it's that far off. So we might be able to get a fairly good prediction out of this model. Note that residuals are fairly small. This suggests that we have a pretty good model for predicting temperature. Okay. So a little bit more about how those plot out. So we conclude that cricket chirps can be used to predict the temperature. The more cricket chirps per minute, the higher the expected average temperature. Our predicted values are off by only a few degrees. Okay, here's some other examples. Imagine predicting annual customer purchases by customer age. That's the example we used in the early introductory video. What about body mass index as a predictor of longevity? What about SAT scores as a predictor of college GPA? You could use credit scores to predict insurance risk. Insurance companies are doing that right now. You can predict employee flight risk, like SQL talks about, like on days taken off as either sick or vacation. And you can also predict like a used car sales price as a function of age. And when we talk about the used car sales price, it's what will the customer pay? If the price is too high, the customer's not going to pay it. If the price is too low, the dealer loses money. So what is the optimal used car sales price as a function of what it was, what worked in the past, what were customers willing to pay in the past? Then we can create a model from that past data, and we can use the age to predict what the best model for the sales price is going to be. So there's just other examples that we can use. And we will, this week, we'll work through one. I believe we're going to use the Boston housing data set to set up our first model using median value. So I will create another video, prepare another video, which actually is going to spend more time in Python in a Jupyter notebook that will show you how to run through that.